Welcome to a session on molecular beams. In this session, we will be seeing what are molecular beams, the experimental production of molecular beams, and also we will be dealing with the applications of molecular beams. Now, let us move on to the topic. Here we will be seeing what do you mean by molecular beams, how molecular beams are produced experimentally, and the applications of molecular beams. Now, you all might have seen a jet of water coming out from any pipe or hose or whatever it is. In a similar way, if the jet in water, we have water molecules coming out, and instead of that, if you are having a jet of molecules, we call that to be a molecular beam, and usually this is observed in vacuum, because in vacuum there are no collisions and all these molecules will be moving in a straight line motion, or you can say that the molecular beam is collimated, all traveling in the parallel paths without any collisions or negligible collisions. Now, this molecular beam, it is actually derived to show the proof for distribution of molecular velocities according to Maxwell-Boltzmann distribution law. And now, up to date, the researchers have developed to such an extent, that is, it has got a wide application in material science and technology, and some of them, I can say that it can be used to design semiconductors, growing thin films with control. We are going to control the thickness and we can control it using molecular beams. Then study the changes occurring at molecular level in reactions or whatever it is, in adsorption and all these things. The changes undergoing at the molecular level can be studied using molecular beams. Now, let us go in detail to the topic. Molecular beam is a stream of molecules. Instead of water, we have a stream of molecules. Though we say molecules, it can be atoms or ions moving in the same direction. See, moving in the same direction with almost equal velocities with a very few collisions. So, they are all going in a straight line in the same direction. Okay. Now, how these molecular beams are produced? They are produced by allowing the gas to expand from a region of high pressure through a small orifice. Small orifice means a very small opening into a vacuum. So, the gas is a molecular beam, that is, it is taken as a gas and it is allowed to pass through a small hole to vacuum when we have the molecular beam being produced. Okay. This was first developed as an experimental evidence for Maxwell-Boltzmann distribution law. We know that Maxwell-Boltzmann distribution laws, that is, we have a range of velocities in a gas molecules, that is ranging from very low velocities to very high velocities, and some of the molecules possessing maximum most probable velocity. This was developed by Otto Stern in 1990, where he used a beam of silver atoms evaporated from solid silver at its melting point. It is a high temperature, that is 962 degrees Celsius. The solid silver is evaporated into gaseous form where we have the silver atoms. Now, this is the experimental setup for molecular beam protection. How will you create the molecular beam? Now, Before going to in detail, you might have seen the word cog wheel. See, it's a cog wheel over here and a cog wheel over here. So, I will explain what is cog wheel and then go for the experimental detail. I have taken a picture from the internet. So, this is the cog wheel. These are all cog wheels. Cog wheels means in the wheels we will be having a depression. There will be a depression, and this depressions, they can allow, if we are giving a beam of light, through the depressions the beam of light can pass. Once it comes over the raised part, here the beam cannot pass through, instead it will get reflected back, retraces its path. Okay. So, this cog wheel is very important because here we have to control the beam of molecules passing through it. Now, this is a source where we have whatever the metal or the required sample is vaporized above its melting point, and it is coming out to this chamber which is vacuum. The conditioner is evacuated. Now, here it is connected to the vacuum pump. So, this chamber is the conditioner's vacuum, and here there is a small orifice or a small hole through which this beam enters this apparatus. Now, the beam is passed through two slits, so that we have a collimated beam, a thin beam of molecules coming out of these two slits. Now, these molecular beam then enters a rotating axle fitted with two cog wheels. Okay, here we have an axle here, okay, connected to these two cog wheels, and this is keeping on rotating. Now, what happens is the cog wheels also rotate along with it. Now, the molecular beam which comes here at the depression of the cog wheel, the molecular beam will pass through. If it strikes on the raised part, that molecular beam will be cut. Okay. So, only those which pass through the depression enters between the two cog wheels. Now, what happens is the molecules that have the same velocity, so that it can pass through the depression of the cog wheel by the other second one, can pass out of this region. That is, if here when it is coming at the raised part of the cog wheel, the beam is cut. So, no question of that molecular beam entering the apparatus further. So, that is cut at this point, and if it is passing through the depression of the cog wheel, that will enter this area. Now, finally, when it reaches the second cog wheel, it should be in such a way, it should be again a depression in this cog wheel. Only then that molecular beam can pass through this slit and reach the detector. This is the detector. Okay, so I will make it clear. Only those molecular beam which has got a velocity, so that it passes through the first cog wheel and reaches the next cog wheel by the time there is a depression in that cog wheel. Only those molecular beams can pass out. They will come to the slit, they get collimated and then strikes on the detector. Hope it is clear. So, the cog wheels are keeping on rotating. If some of the molecular beam reaches here from the first cog wheel, and if it is not striking or passing through the depression of that cog wheel, that molecular beam will be cut. So, actually here what is happening is we are selecting certain molecular beams of a particular velocity to pass through and fall on the detector. Only selected. The others will be cut either on the first cog wheel or at the second cog wheel. Hope I have made it clear. Now, from these, that is what is observed in the detector plus the rotation speed of the cogwheel, taking all these to consideration, you can find out the molecular velocities. Now, you can adjust the rotation speed of the cogwheel, you will get a different molecular beam with different molecular velocity. So, in such way you can continue with a number of molecular velocities, and from the data obtained we have been able to verify Maxwell-Boltzmann distribution law for molecular velocities in a gas. So, this is an experiment in which we have been to prove that the molecular velocity distribution suggested by Maxwell-Boltzmann is true. Next, we will go for the applications. The first application is molecular beam epitaxy. It is also mentioned as MBE, molecular beam epitaxy. It is actually, this word is derived from Greek words. Epi means above, taxis means in an ordered manner. That is, the layers are being constructed in an ordered manner, one above the other. That is the word epitaxy means. Now, by definition, epitaxy is a process of crystal growing. It is a process of crystal growing. We know that when we evaporate a solution of an crystalline substance dissolved in it, on evaporation, depending on the rate of evaporation, the type of crystal you are obtaining will be different. Okay. Now, in a similar way, you can grow, that is slow evaporation, you will get larger size crystals. In a similar way, epitaxy is a process in which we grow crystals, which involves formation of new crystalline layers on a substrate. It forms new layers. First, we will have a substrate, over that we will create one layer. After that, we will create the other layer. In such a manner, in an ordered fashion, we will be creating layer by layer and we will grow the crystal. When molecular beams are used to deposit extremely thin layers of material onto a substrate, we call that to be molecular beam epitaxy or MBE. The crystal growth is done with the help of molecular beams. So, we are having one layer of molecular beam on the substrate, then again another layer, and this building up is known as molecular beam epitaxy. Now, here molecular beam epitaxy enables to create complex semiconductor structures used in electronics and optoelectronics like quantum wells, superlattices with a control over composition and thickness. That is, we are under the control, we can control the composition and thickness of these semiconductor structures. And quantum wells, you know, it is at the molecular level. Okay. Now, see, this is a picture of epitaxial layers growing on a substrate. We have a substrate over here, and over that, by forcing molecular beams, that is, molecular beams are allowed to fall on the substrate, and you are creating the layers of molecules which form the crystal layer. See, there is a substrate. This is one set of molecular beams which has already been placed, and over that again we are giving the molecular beams, and then we are controlling the thickness and types of molecules to be added along the layers. This is a epitaxial growth, which is a schematic representation. Of course, because we know that molecules are not visible to our naked eyes. Dear students, now we will see a 3D animation video which I will be using here for just giving you a brief outline, like how the molecular beam is used for molecular beam epitaxy and the molecular beam epitaxy process, okay, and that is for metal oxides. Now, I thank Dr. Bharat Jalan for giving me consent to use this video, which has been created in their lab of Department of Chemical Engineering and Technology, Minnesota, US. You can see that it is a very beautifully made 3D animation in which we have the minute details which is given as a description as captions. There will be introduction of the substrate, heating of the substrate, deposition of molecular beams of different types, and doing the molecular beam epitaxy. Next is spectroscopy. Its application in spectroscopy is molecular beams cannot be used as such. It should be combined along with other spectroscopic methods and used to measure energy levels of atoms, molecules, providing detailed information about their structure. Because molecular beams means they are very small particles, and using these particles we can combine it with spectroscopic methods, and then you can measure the energy of atoms, molecules, and also we can get the information of their structure, and it is not simply the information of the structure at the molecular level, or you can say at the basic level of any substance. Okay. Next is chemical reaction mechanism. We know that chemical reactions, they are reactions between atoms, ions or molecules. Molecular beams can be used to observe the changes of reacting molecules at the molecular level. It's very informative. At the molecular level, what we observe is generally the changes taking place, or we will assume that the changes has been taking place by getting the results or the products. Here it is not like that. Using molecular beams, we are observing the changes of the reacting molecules at the molecular level itself, and thereby providing a detailed information about the reaction mechanism. So, it will help a lot in studying the reaction mechanism, and we get a detailed information at the molecular level using molecular beams. So, that is the application in chemical reaction mechanism. Next application is in the surface studies. We know that adsorption, one of the surface phenomena, this is surface phenomena, and we have some quantitative equations and laws regarding adsorption. Now, here we measure the external parameters, like we can measure the surface area, then porosity and all those things. But at the molecular level, it is very difficult. For adsorption being a surface phenomena, if we can see the process undergoing at the surface at the molecular level, you can be sure like what is the process undergoing. Is it exactly adsorption, or it is partly adsorption and adsorption? All these can be studied. See, by observing the interaction of the molecular beam with the surface of any material, its surface properties like adsorption, and it is a desorption means, adsorption means there is addition or accumulation at the surface. Desorption is the opposite of adsorption, that is it leaves the surface. Okay, that is desorption. Catalysis, we know that catalysis also is a surface property. Therefore, the reaction taking place mostly, not in all cases, mostly in solid catalyst, it is on the surface reactions occurring. So, you can study the mechanism of catalysis. Now, another factor is surface scattering. All these can be studied, all these surface studies can be done with the help of molecular beam. Next is determination of molecular velocity distribution. The measurement of time taken by the molecules to travel a known distance in a molecular beam can be used to determine their velocity distribution. This I have mentioned it in that experimental procedure itself, like how the molecular beam is traversing or traveling between two cogwheels, that will be the distance, and how and what are their velocities. You find that and you can determine the velocity distribution, and can be used for the verification of Maxwell-Boltzmann distribution law. Last one is the measurement of magnetic moments. Magnetic moments of the constituent particles, that is at the molecular level, can be studied by applying magnetic field to molecular beams. We know that whether you can find out whether the molecule is paramagnetic, diamagnetic, or whether it is ferromagnetic, all these can be informations can be derived by measuring the magnetic moments. And for that, you can take the molecular beam of particular substance and applying magnetic field to that, you can find their magnetic nature. To conclude, we have been seeing molecular beams and production of molecular beams, that is the experimental method in which we will just refresh it. See, this is a setup, it is a schematic representation in which the substance whose molecular beam has to be studied is evaporated at its melting point, and the vapors are passed through a very small orifice into a region of vacuum. Okay, it passes through the slits so that we get the collimated beams, and they are allowed to pass through rotating cog wheels in order to select certain molecular beams of particular frequency or velocity, which then falls on a detector, and from that you can calculate their velocity distributions. Okay, that is a molecular beam experiment, and then we go for the applications. It is a molecular beam epitaxy. As we have seen, it is a building up of crystal layer in which we are going to control the layer, the thickness of the layer, the composition of the layer in building up the crystal, and that is by taking molecular beams. Okay. So, that is molecular epitaxy. Then in spectroscopy, you can find the detailed informations at the molecular level using molecular beams, along with it is coupled with spectroscopic methods to get the details at the molecular level. Then chemical reactions, we know that it already occurs at the molecular or atomic levels, and these can be observed using molecular beams, and thereby we get an idea about the reaction mechanism. Next is surface studies application, where adsorption, desorption, catalysis, surface scattering, all these can be studied by taking the molecular beam and allowing it to interact with the surface of the material required. Then comes the determination of molecular velocity distribution, that is our Maxwell-Boltzmann distribution of molecular velocities. This can also be studied by taking the time taken by the molecular beams to travel a known distance in a molecular beam, and then we can find out the velocity distribution. And the last application is the measurement of magnetic moments. The magnetic moments gives an idea about whether a substance is paramagnetic, diamagnetic or ferromagnetic. This can also be studied by taking a molecular beam of required substance and studying their magnetic properties by applying magnetic field to that molecular beams. And that is all for this session. Thank you.